Hi and welcome to Introductory Physics. Today we'll be talking about kinematics and all things motion. Today let's cover what really is motion, how do you quantify it, and all the different aspects that come into the picture when we study kinematics. So to set the scene, recently my sister ran a 200-meter race in the state championships. How do you think the race went? It wasn't a full dash of 200 meters. It starts off slow. For at least the first 100 meters, you have all of the participants running at a decent pace. They start off slow, they build up speed, and suddenly at the last 100 meters, they dash. They accelerate and accelerate and accelerate till one reaches the finish line. And then you know what do? They slow down. They slow down till they reach a stopping point well beyond the 200 meters. So this imagination that you might have made of a runner starting slow, picking up pace, and then accelerating beyond belief, and then again slowing down is genuinely what motion is all about. Kinematics is the study of motion without worrying about what are the causes behind that motion. We're just studying how things move. That is what kinematics is all about. Here we'll be asking how far did something move, or how fast, how did they speed up, did they slow down? And interestingly also, what does that look like on a graph? In this story, motion is everywhere. Starting slow, accelerating, maintaining that speed, and even slowing down. But here's a twist. How you see that motion is pretty much dependent on where you exactly see that from. That's something called as a frame of reference. Imagine that you're on a train and you are going at a good 120 miles per hour, and there's another train going beside you. For that split second, it might seem that the train is stationary, that the world is glitching. But that is the power of a frame of reference, where depending upon how you experience motion, you see these different parameters, you experience motion differently entirely because of where you are seeing it from. Say as an example, you're running, I'll stick to the same example, you're running that entire 200 meters race. When you're starting slow, suddenly the world seems like it's moving behind you. When you speed up, it feels like it's speeding up and moving past faster than you can imagine. But who's right? Are you right to say that the world is moving behind you? Or someone like me in the audience who's saying that no, the runner is moving past? I would say both are right, because both are looking at it from different frames of reference, yet their understanding of motion is accurate to that frame of reference. Speaking of frame of reference, there are two kinds that you must keep in mind. You will go into more detail into all of this once you are studying this entire topic in higher classes. One is called as an inertial frame of reference, the other is non-inertial. Here, in this case, we are looking at, if I am the one watching the race, I am in an inertial frame of reference where I am not accelerating. Either I'm in rest or I'm in uniform motion. In this particular case, I am in rest. A non-inertial frame of reference will be where the acceleration is varying. In this example, it would be the runner, because the runner starts off slow, then picks up pace, and then again slows down. The acceleration has changed over time, and thus their experience of the motion around them also changes. So now whenever you look at motion, it is extremely important that you consider the frame of reference, because that significantly changes how you experience motion. So whenever you have something around you, whether you're sitting in a car or you're waiting to cross the road, think about the frame of reference with which you're observing the car move. That is the first step to understanding kinematics as a whole. Let's go back to the 200 meters race. Say we start at a 0-meter mark and we are running up to the 200-meter mark, the finish line. How much distance did my sister cover? Logical, 200 meters. But say, to get a feel of the track, she starts up at the finish line, she jogs back 50 meters, then came back to the starting line, and then started the race. So what's her distance now? I would say I'm adding 50 meters, I'm going back to my finish line, I move to the starting line, and then I run the 200 meters. It's that 50 plus 200, that's 300 meters of distance. But what's her displacement? Displacement, pretty simply, is just where do you start to where do you stop, and what's the shortest path between those 2 points. As simple as that. If this 200 meters race was on a straight track, her displacement would have been 200 meters. But a homework for you people, a 200-meter race is never on a straight track. There's a curve, because you have your athletics track being this nice oval. So look at the general measurements and now try and measure what would be her displacement. So again, to simply differentiate between distance and displacement, distance is how much ground you have covered, whereas displacement is what's the shortest distance between the starting point and the ending point. Now, what's interesting is the type of quantity that these two are. One's a scalar, one's a vector. Distance is your scalar, displacement is your vector. Before we proceed, it is important for you to understand the prerequisites for this lesson. You need to understand what are scalars and vectors. You need to be able to do vector algebra. Once you are done with this, then only you must come to this lesson today. Now, once you've had distance and displacement, now we can define something called as speed and velocity. Speed is distance over time, velocity is displacement over time. Logically, speed is a scalar and velocity is a vector. Whenever we are dealing with kinematic calculations from this point forward, we'll be exclusively dealing with vectors because yes, the direction in which the motion is occurring is extremely important for us. Now, in our example of my sister running, at that 100-meter mark, all of the runners pick up pace. All of them increase their velocity. This change in velocity with time is what we call as acceleration. And when she slows down after the finish line, that is still in all technicalities acceleration, but in the negative direction, or what we generally call as deceleration in regular language. Let's try and better understand this motion now with this knowledge that we have. Say if I'm plotting a graph of displacement versus time, and assume that this 200-meter race is occurring in a linear fashion. What do we observe? A simple straight line going from 0 to 200 along certain time. But now, if we try to calculate a velocity time graph, that's no longer linear because the velocity starts off slow, it stays consistent, then again picks up, and then stays consistent and then goes down. So at each and every different point that we can visualize, there is a different slope. And what do you think the slope of a velocity time graph gives you? Velocity over time, that's acceleration. So at these distinct regions, you can visualize different amount of acceleration that the runner possesses. Let's recap till now whatever we have studied about motion. Distance is how much ground you have covered. Displacement is the shortest path between the starting and the ending point. Speed is distance over time. Velocity is displacement over time. And an acceleration is velocity over time. We've got the words, we've got the visuals. Now we'll bring in the numbers. Before we proceed, this is a sneak peek into the Introductory Physics program for grade 11. We run similar programs for physics, chemistry, bio, and mathematics for grades 9 to grade 12 at Learners Club. If you're interested, what we do is we create personalized learning programs and plans for each and every learner who studies at Learners Club to meet their learning goals by mitigating their learning challenges. If you find yourself interested in knowing what we do, and if you found whatever we have done till now interesting and insightful, you can get your current learning methods and plans audited from us and our top mentors like me by scheduling a call with us. The link is in the description. On that free call, what you get is one-on-one time with our expert mentors who can analyze each and every step of your learning journey and give you exact advice and analysis of how you can improve entirely for free. Again, the link's in the description down below. And if you're interested in checking out all of our other services, you can go onto our website. That link is also in the description below. Now, without further ado, let's get back into the lesson. Okay, imagine that you're riding a bike and you're going at a staggering pace of 20 kilometers per hour. And you notice that there's a sign that says that there's a speed breaker in 100 meters. Of course, you need to slow down gradually. How do you know when to brake? Rather, how do you know how much distance do you need to decelerate from 20 kilometers per hour to 0? That can be simply calculated by the equations of motion. The golden equations for all motion with uniform acceleration. Please keep this in mind. The equations of motion are perfect for all motions with uniform acceleration. To simply solve this, you consider your current velocity as an initial velocity u. Your final velocity will be the one which you will have at rest, which is 0. We need to know how much time you will take to reach that point, and assuming constant acceleration. So a simple equation that we use is v is equal to u plus at. Now we want to know the distance. There's a very simple equation called as s is equal to ut plus half at squared. Here we look at initial velocity, the time that you will be taking to cover that distance, and the acceleration with which you're going. If you do not have time in your problem, but just initial velocity, final velocity, the distance that you cover, and the acceleration, your third equation v square is equal to u square plus 2as is perfect for that. Let's solve a question to get a better understanding of all of this. A car starts from rest and accelerates uniformly at 2 meters per second. What is the velocity after 5? We are starting from rest, so u is equal to 0. We are accelerating uniformly at the rate of 2 meters per second square. Your acceleration is 2 meters per second square. We need to know the velocity after 5 seconds. T is given as 5. You have u, you have a, you have t, and you need to find v. Simply we use the first equation, v is equal to u plus at. Substitute the values, you get your answer as 10 meters per second. Now, say if I want to know the distance that you have covered within those 5 seconds, you have u, you have a, you have t. Put it into the second equation of motion and you get your s as 25 meters. This is simply how you solve all of this. Now maybe let's derive something. Let's take we know that the acceleration is the rate of change of velocity by time. So we can substitute a is equal to v minus u by t, rearrange the equation, we get v is equal to u plus at. Let's compare this to the standard equation of a linear graph, y is equal to mx plus c, where you can kind of see the similarities. Your m usually stands for the slope, which can be corresponding to a in our first equation of motion. That's how we understand that the acceleration is the slope. We also know that displacement s is equal to the average velocity v plus u by 2 into time. Now this form that we have, s is equal to v plus u by 2 times t, if we plug in v is equal to u plus at over here, what we get is pretty interestingly s is equal to u plus at by 2 times t, or 2u plus at by 2 times t, or simply ut plus half at square. That's our second equation. And our third equation is not that difficult to get. From our equation 1, we know that time is equal to v minus u by a. If I substitute this into equation 2, I get s is equal to u plus v by 2 times t, which pretty much now equals to u plus v by 2 times v minus u by a. Now I have v plus u, v minus u in multiplication. I use my identity to get v square minus u square by 2a, and rearranging this, what we get, v square is equal to u square plus 2as. These were simple derivations to these three equations that you must know for your board exams particularly. With all of this in mind, let's try and tackle some interesting phenomena that we regularly observe within our world. Now let's say you're on a train and you're moving at a decent pace, and you notice that another train is going with you, the same example as previously, and you feel that the train beside you is just not moving. What's happening? Is the train at rest? Are you at rest? Or is the world glitching? Not at all. This is relative motion at play. As I said previously, motion is experienced differently depending upon how you look at it. So looking at different frames of reference can change our experience of motion, and that can be quantified. Let's say car A is moving at 60 kilometers per hour and car B is slightly ahead of it at 40 kilometers per hour in the same direction. To someone standing on the road, both cars are moving ahead. But to car A, which is moving faster than car B, it will feel as if car B is moving slightly backwards. So now we can define VAB as VA minus VB. Velocity of A with respect to B is A's velocity minus B's velocity. Remember, this sign convention is extremely important, because I don't want you to mug up these formulae for which direction what is moving in what direction. When you have both of them moving in the same direction, consider the values as positive. So when you substitute it as VA minus VB, no sign changes. Say now it's in this other direction. So now you have the car B moving 40 kilometers per hour in the opposite direction. Then you change the sign of VB. So now the equation becomes VA plus VB. If you're in the same direction, same sign. If you're in the opposite direction, opposite sign. And then only you will adjust the formula. Do not mug this up. So now let's take up a question. If train A and train B are moving on parallel tracks in opposite directions, train A at 60 kilometers per hour and train B at 90 kilometers per hour, what is the relative velocity of A with respect to B? Look at how this question has been framed. What are we supposed to find? Velocity of A with respect to B, VAB. Now, VA minus VB is our regular formula. But what did I tell you? These are moving in opposite directions. So you change the sign of B, it becomes VA minus of minus VB or VA plus VB. 60 plus 90, 150. So to train A passengers, train B will feel as if it's approaching them at 150 kilometers per hour. That is the relative velocity of train A with respect to train B. Now, if we had to calculate the velocity of train B with respect to train A, what changes is VB minus VA. Again, it's B with respect to A. The direction of A is different from that of B. You put a negative sign. So now what happens is VBA is equal to VB minus of minus VA or VB plus VA. Again, simply you add 60 plus 90 or rather 90 plus 60 and you get 150. Even to train B passengers, train A will seem like it's moving at 150 kilometers per hour. Now, let me ask a follow-up. Let's say both trains are 200 meters long. How much time will they take to completely cross each other? This is a very typical question that gets asked in a lot of competitive exams, so pay attention to it. Both trains are 200 meters long. So when they're approaching, the overall distance that they need to cover is 400 meters. Now you have relative velocity of 150 kilometers per hour. When you convert it to meters per second, you get up to 41.67 meters per second. Calculate, you have the distance, you have the velocity, calculate the time, it comes to around 9.6 seconds. So, this idea, using relative velocity to calculate how much distance will be covered is important. A lot of questions get asked about this. Let's wrap up today's session with a couple of problems. But till now, what you have learned is you have learned that motion is the change of position with respect to time. You have learned frames of references decide how you see that motion. Distance and displacement measures how far something moves. Speed, velocity, acceleration describe how it moves. Equations of motion let you calculate exact outcomes when the acceleration is constant, and relative motion helps compare the movement between two observers or objects. Let's solve a question. You're driving a small car and you're going at 54 kilometers per hour. Ahead of you is a bus in the same direction at 36 kilometers per hour. Your car is initially 20 meters behind the bus. The moment you start accelerating at 2 meters per second square, you try to overtake. How long will it take you to overtake the bus completely? And what distance will you cover by then? Very interesting problem. We'll break it down slowly and steadily. You've been given your initial velocity of 54 kilometers per hour. Let's convert it to meters per second. That's 15 meters per second. The bus velocity has been given, which is 36 kilometers per hour. That comes up to 10 meters per second. You are in the car, so we are going to be using relative motion. Your frame of reference is in the car, so you will be using relative motion always. So you are supposed to cover around 20 meters. And the length of the bus, let's assume it to be 10 meters, is to also be overtaken. So your total relative displacement is 20 plus 10, that's 30. And your initial relative velocity with respect to the bus will be your velocity v minus v bus. Now bus is going in the same direction, so you do not change the sign. That's 15 minus 10, that's 5 meters per second. So this v relative is what we'll be using to calculate. And your car is accelerating at 2 meters per second. So U is been given as 5 meters per second, S is given as 30 meters, and A has been given as 2 meters per second square. We need to find the time. So substitute all of this into the second equation of motion, you get time to be around 2.5 seconds. Now, if you want to calculate the distance covered, you look at the frame of reference of someone standing outside the car on the road. Here we do not use the frame of reference of the car. We want to see the actual distance that the car covers while trying to overtake. So what we do, now our U is 15, A is still 2 meters per second, and the time that it takes is 2.5 seconds. So substituting that into the second equation of motion, we get 43.75 meters. In just one question, we use frame of reference, relative motion, unit conversion, displacement and velocity, acceleration, equations of motions as well. With this, we will be wrapping up this tutorial on kinematics. Part 2 will come soon, so stay tuned for that. Again, if you found this extremely insightful, make sure to hit the like and subscribe button. And if you want to sit with me and our top mentors and audit your learning and understand how you learn the best, the link is in the description. Schedule a free call today. With this, we will be wrapping up our tutorial. I will see you the next time. Learn more at Learners Club.